All right, welcome back, high school physics. Today we're going to talk about projectiles. Very specifically, we're going to focus on horizontal projectiles. But before we do that, I want to go to this simulation program we've used before called Algodo, and this simulation program just helps us physically kind of see objects, and this does a pretty good job of graphing for us. This is basically two created objects I've put here, and you can change a lot about it. I put tracers on it so that you can kind of see the object as it kind of moves through the air. You can kind of tell where it's been. And really that's just going to be for a purpose here in a minute to kind of show you. But both of these objects fall. So I'm going to hit play, and they're going to fall toward the ground. And you should notice that as they fall toward the ground, this is free fall, their velocity is increasing as we fall. This is just graphing the one on the left, but the object is accelerating downward. In fact, if we look at the slope of our velocity versus time graph, we can see it's negative 9.8 meters per second squared. That is showing the acceleration downward is what we think of in terms of gravity. Both objects are going to hit the ground at the same time and bounce back up, and we'll get to the whole collision side of things later. But I'm going to back these back up, and we're going to talk about something for a moment here. The question is, and this is kind of a good myth, Mythbuster did this before, but if you were to drop a ball or a bullet, let's say a bullet, at the same time that you fired a gun to the right with a really fast velocity, the question is, would the bullet that's dropped and the bullet fired from the gun, would they hit the ground at the same time? So I'm going to try to simulate that a little bit here. What I'm going to do is I'm going to put a velocity to the X direction. So it's fired horizontally. I'm going to put it at about, I don't know, 6 meters per second. And so what happens here, I'm going to back it out a little bit so you can kind of see a little bit further. But if I hit play and the one on the right is going to be fired horizontally and the one on the left is just going to be dropped, let's see if they hit the ground at the same time. Boom. They both hit the ground at the same time. And you're thinking, well, that bullet's not traveling fast enough. If it was traveling a lot faster, it wouldn't hit the ground at the same time. So here's what I'm willing to do. I'm willing to go back to this one on the right, and we're going to make the velocity as great as we can in the X direction, 25. Probably need to back it up just a little bit so we can see a little further out. But here's what we're going to do. We are going to hit play, and the bullet on the left drops, the bullet on the right is fired to the right as fast as it'll let me do, which is 25 meters per second. We're going to watch and see if they hit the ground at the same time. Boom. And it looks like they do hit the ground at the same time. And that's a little bit of an interesting phenomenon. But here's what you have to know and understand in perspective is that the dropping of the ball or the bullet at the same time the one is fired horizontally, the only thing acting on those two objects is gravity. Gravity is acting on both objects in the same way. It's accelerating them downward at a rate of 9.8 meters per second squared. Since one has horizontal velocity, it travels further. So when we talk about how far the object travels, this distance from here to there, so where it's launched to where it ends up hitting, we call that the horizontal range. So how far the projectile goes. We'll talk about that a lot, but the time it takes for it to fall, whether it's dropped or shot to the right, is the same, which is awesome because here's what we can do. We can treat a projectile by splitting up the X components, the X velocity, the X direction. We can treat that separately than the Y direction. So our horizontal projectiles are basically going to act as if we just drop an object to calculate all the Y information, and then we will deal with horizontal motion separately. Okay. So we're going to go to our PowerPoint here, and I want you to kind of look at this. And I'm going to kind of highlight some details, and then I'll work a problem with you. Object moving in 2 dimensions under the influence of gravity. That's what a projectile is. Since motion is in 2 dimensions, the X dimension, the Y dimensions, we are going to break up our motion into X components and Y components. We got to keep them separate. The reason why we have to keep them separate is because in the Y direction, we have acceleration, right? In the Y direction, we have acceleration. It's downward. However, in the X direction, since there's nothing really acting in the X direction, we actually have constant velocity. We have no acceleration. So we have to treat the X and Y separately. In fact, we'll usually make a chart and we put everything related to the X and we'll keep it separate than the Y. The Y component, when we're dealing with Y, we're going to use the gravity to be negative 9.8 or negative 9.0 meters per second squared. One thing to mention when we talk about describing the motion of a projectile, let's say I have a table and I shoot an object off the table this direction. The motion that that projectile travels is really kind of this parabolic pathway downward to the right. And so velocity of a projectile, there's really two things that we can deal with. We can deal with the X velocity and we can deal with the Y velocity. The X velocity is always constant and the Y velocity is always accelerating downward at negative 9.8 meters per second squared. Okay. If we wanted to kind of describe any point in terms of thinking about its velocity as it travels along this path here, at the very beginning, it has an X velocity this way, but it has no Y velocity. So I'm not going to draw anything on that. If I put another dot along its pathway, our X velocity is constant, but we have a little bit of a Y velocity downward. And if we follow this pattern, the X velocity always should be the same length. It's constant. However, the Y velocity gets bigger as we go down in terms of our picture. That's supposed to be Vy. Okay. So notice the arrows that we're drawing here, the vectors, they get bigger for the Vy as we go down, but the Vx should stay constant, okay? So this is kind of the basic idea of projectiles. We're gonna have to keep the X and Y motion separately. So what I'm gonna do is just work a problem with you, and I think you'll make sense of this. So we have a horizontally launched projectile. Again, this is basically the ball launched off to the right. The X velocity doesn't change. The Y velocity starts out as 0. This is just like an object being dropped, okay? So we have a projectile launched from the top of a 25-meter tall building horizontally at a speed of 15 meters per second. Here's the three things we're gonna find. First of all, how much time is the projectile in the air? Time, that's called time of flight. Second, how far does it travel distance-wise from the base of the platform where it's falling from? So that is, we call that horizontal range. And then the other thing we're going to do is we're going to find what is the horizontal velocity when it lands, and then also what's the vertical velocity when it lands. Okay, so we'll break this up into parts here. So here we go. Here's our parts. It says a projectile is launched from the top of a 25-meter building horizontally at a speed of 15 meters per second. If I want to record the time of flight, here's all I do. I'm going to think in terms of Y direction only. Okay, so this is no different than me dropping an object from the top of a building that's 25 meters tall. So this just becomes a free fall problem of dropping an object. And if we can figure out how long it's in the air, that's how long it's going to be traveling also horizontally. So we start out and we say, what's my initial velocity in the Y direction? Well, if it's going off horizontally, it has no Y velocity at the beginning. So it starts off with a velocity of 0 meters per second. The acceleration is downward is negative 9.80 meters per second squared. We know the delta Y, the change in position, we're going to say it's negative 25 meters because that's how much it falls. From the perspective of falling, it's actually negative 25 meters. First thing we're going to do is find T, right? So we look for an equation. This is kinematics. We go back to our equations with T, and we know that there's one that puts all of this together. It's a matter of finding our equation and noticing that VF does not show up in our equation. So I'm going to go with this equation right here. Delta y is equal to v sub 0 yt plus 1/2 at squared. Okay. Now notice, because my initial velocity is 0, I can cancel that term. And I'm going to rearrange this. We did this before. 2 times delta y divided by a, and then we're going to get t by itself. So we square root it. So I went through a couple steps here to get t by itself, and then I square root it. So we're going to take the square root of 2 times negative 25 meters over negative 9.8. And when we punch this into a calculator, 8 times 2 square root, you get 2.26 seconds. So that's how long it's in the air. That's how long it falls. Now, if it's falling for 2.26 seconds, it's also moving horizontally for 2.26 seconds. Since this is constant velocity in the x direction, then this becomes a really easy problem. We know the velocity is 15 meters per second. The time is 2.26 seconds. So the question is, what is the displacement? Well, we have an equation for that. Remember, velocity is just displacement over time. So we can do Vx times t, and that's going to give us our horizontal displacement. So we take our 15 meters per second, and we say, okay, it's traveling 15 meters per second for 2.26 seconds. So we multiply these two together, and we get 34 or 33.88 meters. Okay, so we are treating the x and y separately. Now, how do we know the horizontal velocity when it hits the ground? This is really all about the horizontal and vertical velocities of the projectile when it lands. I think I forgot to type that. When it lands. Okay, first of all, since the horizontal velocity is constant, it still has a 15 meters per second horizontal velocity. It's constant, right? Now, in the y direction, we have to kind of go back to our object falling again, right? We know the initial velocity is 0 meters per second. We know the time now is 2.26 seconds it falls. We know the acceleration is negative 9.80 meters per second squared. We also do know delta y is negative 25. And the only thing we don't know is VF, right? And that's what we're trying to find. So VF, you got a lot of equations we could use. We're going to use AT plus V sub 0. That's probably the easiest one to use here. So I'm going to go back and say, okay, well, I know that my acceleration is negative 9.80. I'm going to accelerate for 2.26 seconds. My initial velocity was 0, so that goes away. So we take negative 9.80 times 2.26, and we find that we have a negative 22.1 meters per second is our final velocity. The negative sign just tells us it's downward. We have a negative velocity, okay? Now, we could put this, if we really wanted to, we could go back to vectors and we could find out what angle it hit with. We would just take and make a right triangle with the x component and the y component, draw the right triangle, find the resultant, and find the angle. I'm not going to have you do that.